Hey everyone, welcome back to my channel EduVibe. In today's lesson, we are moving to the next topic of the atomic physics, which is a continuity of the previous topic, which is radioactive decay. Now we're doing the types of the radioactive decay, which is very important topic. So because we are just doing the all the types of radioactive decay with the theory part. Now we're doing with the some part where we involve the type of the reactions, type of the equations we want in the every decade. So let's start with eradicate some laws we have to know in this. Eradicate obeys the laws of conservation of momentum and the energy. Furthermore, there are above two additional conservation laws. So they eradicate obeys the law of the conservation of momentum and energy, and also the conservation of charge and the conservation of the nucleons. That both laws can also be obeyed by the radioactive decay. So conservation of charge, the net radical charge cannot change in a decay process. The total charge of the reactants must equal to the total charge of the products. This is the physics principle 7. So total charge in reactants must equal to the total charge of the products. That's the thing, they didn't change that net radical charge. Next, we have a conservation of the nucleons, that the total number of nucleons of the final products must be the equal to the total number of the nucleons of the reactants. This is the phase principle 8, and they're talking about the total number of nucleons remains constant. So in the final product or in the reactants, the number of total of the nucleons remains constant. They are equal in both sides. So how they are equal? We have some how can we like doing that thing. So in the like alpha decade, beta decade, or the gamma decade, you get these types of equations. You can see that these are the isotopes. So the PO, this PB, and then alpha. So this is alpha decade, and this one is also the alpha decade. But we're not doing the types particularly. Now we're just finding that the are the following decades processes possible or not. How can we say that it is possible to find the number of nucleons before and after the reaction? So firstly, talking about the reactant side. So reactant side, how many nucleons we have? So we have only this one. So this upper thing denotes the number of nucleons. So it's 214. So the number of nucleons is 214 is equal to, there is 208 and then plus with 4. So when you calculate this, you get this, which is not equal. This must be equal on both sides. So this decade is not possible. That's the thing. In the next one, we have the two things. So again, there we have a 230 is equal to 226 plus 4. You get 230 is equal to 230, which says that it is possible. It is possible. And decay 10 a lot. You can also check that up the downward down thing, this one. If this is also it also should be equal. So this is atomic number, and atomic number should be equal to, so 90 is equal to 88 plus 2. So where 99 is equal, 90 is equal to 90. So that's the thing, that the both things should be equal on the both sides. So that's why you have to check this. So in the other cases, sometimes you have to complete the rest of equation, so we can take care of that things, that the both the charges, new number of nucleons, atomic numbers on the both sides should be equal, like this. So this is just an example. We are moving to the now actual alpha decade and all the things. So firstly, we have alpha decade. So atoms, like people, crave stability. Heavy nuclei that are unstable will be an electromagnetic force repelling the protons almost as greater as the attractive strong force holding the nucleus together. So we know that attractive strong force is there, which holding the nucleus together. So these nuclei will spontaneously emit two protons and two neutrons that bind together. We discussed that already in the strong nuclear force lesson. This would be the same as the helium nucleons. So the helium nucleus is same as the nucleus that bind the two protons and two neutrons without the electrons. However, because the nucleon is born from the another nucleus and not the natural helium like from the air, we refer to a collection of the protons, and the neutrons is the alpha particles. So this whole the definition of that. Because of that, your nucleus is not born. This is an come from the another nucleus, which is not a natural helium like from the air. So this refers to those collection of the protons, and the neutrons is called the alpha particle. So we doing the things with protons and neutrons in this. Rutherford made the discovery in 1908 that alpha particles are helium nuclei spontaneously emitted from the unstable heavier nuclei. So this is again the discovery of the Rutherford in 1908. The alpha particles are the helium nuclei spontaneously emitted from the unstable and the heavier nuclei. And this is the general form of to write the alpha decayed equation. So you have some element over there. So you have some element over there. You have when the reaction occurs, you have another element, but your alpha remains 4 and 2 always. But your a from here, this a minus 4 in the other side, and then z going to z minus 2. Then we have a 4 and 2 of alpha. So that's the equation you can follow when you have any example of this. So your H is a chemical symbol for the parent element, the original element of the decayed process, which is in the right hand side. Y is a chemical symbol of the daughter element, the element produced by decayed process, which is in the product side. So write the alpha process, alpha decayed process for the uranium 238. So there is a uranium given to us. So uranium has a symbol of U, and we have a 238. This is the element number, atomic number of 92. And when the reaction occurs, so you have to do 238 minus 4, which will you get 234. And 92 minus 2, you will get 90. So now you have to check in your periodic table that which element has the atomic number of 90. So it's theronium, which is TH, and plus complete digression with alpha 42. So this is type of equation you can make from the anything. And sometimes you have to make the equations in your questions, but like very rare cases, not in every time. That thing you have to do in the MCQs form, that from the 4 options you have to say that which is correct for the alpha decayed process. So there is one of them. So this is the right thing, and you have to know this and alpha decayed all the things. Next, for beta decayed, as you all know, beta decay has of two types, beta positive and beta negative. So they are both have the different processes to make the equations of this. So firstly, we're doing some theoretical part in this. So looking at the beta decayed, we need to look at two separate decay types, beta negative and the beta positive. So firstly, we have a neutron. So what is a neutron? So in the beta decayed, we have something called the neutron as a product. When you make the equation, I will tell you that we have something called the neutron and we have an anti-neutron. So neutron in the beta decay, the daughter nucleus is generally much more messier than the beta particle. This means the daughter nucleus has very minimal recoil, and most of the kinetic energy should be transferred to the beta particle. So in the beta particle, you have a daughter nucleus and generally more messier than the beta particle. So it means that daughter nucleus are very minimal recoil then. So most of the time, kinetic energy should be transferred to the beta particle. That's why we're using the neutron neutron thing. So the neutron is an elementary particle that interests only by the weak nuclear force. So if we have a weak nuclear force, then this neutron can be a threat. This is elementary particle. And the force of gravity. It is electrically neutral and is initially believed to have no mass. This have no mass. This have the mass, but with very small mass. So we can say there's a no mass, and this is a neutral. And you have to take off that thing, that which thing is neutral and which is not neutral. The mass of the neutron is difficult to calculate exactly at the present time. The best estimate of neutron mass is this. This is very small, 2.15 10 to minus 37 kgs. And that EV per c square is the one form we have to discuss later on lessons. And that is the very smallest thing. You have to just know the theory of the neutron. Now, the beta negative decay. In a beta negative decay, the nucleus has too many neutrons to stable. Thus the nucleus emits the neutron. So in the beta decay, the nucleus has too many neutrons. Because of too many neutrons, the nucleus then emits the neutron, which will transform into a proton due to the weak nuclear force, and which is reabsorbed into the atom and an electron and an extremely small particle known as an anti-neutron. So this is the form of, this is like a symbol of the anti-neutron. This involves in the beta negative, and the neutron is in the beta positive. So this is as a product can release. So there's a three thing mentioned that one we have a when we have this anti-neutron, one we have the beta, this is negative, so this is always be there, and we have this. So it's X if A and Z, so A in the product side will remains A, then Z goes to A plus 1 because you have a minus 1 over there. This is beta negative, so we take it minus 1. So the electron that is emitted from beta negative case is referred to beta negative particle. We usually refer to as a bit by this distinguish the fact is that electron that originate from the nucleus, not on a electron that is orbiting the nucleus. So you have to just know the equation and some theory that which things are involved. This is the weak nuclear force, and we have this thing called the anti-neutral, which is very extremely small particle. So we have to make the decay equation for iodine 131 undergoing the beta negative decay. So the same thing we do it in the alpha decay. So we have 131. This is the atomic number of 53. And when the reaction occurs, so we have 131 remains 131. 53 plus 1 we get 54, and at 54 we have a axionium plus this thing plus this thing remains in your thing. So that's all thing. You have to not forget this sign, because this sign represents this is the anti-neutron, not the neutron. That neutron neutrino we made in another thing. This is a neutrino. Then we have a beta positive decay. The beta positive decay, the proton will transfer into neutron. Due to the weak nuclear force again, we now have a proton. So this is again the same thing that the antiparticle, but this is called a beta positive particle and a neutrino, and the simplified process for beta particle is the case. So A and Z at the product side, A remains the same. The Z now do -1 because this is a positive. And we have 0 and 1, and we have a neutrino. The prostrino is the antiparticle of the electron. So there's something about the brief analysis of the prostrino. So prostrino is the antiparticle of the electron. We discussed that in the later on lessons, that that every neutron, proton, so everything has some antiparticle. It has all the same properties of the electron except of the charge. The charge is positive because electron has a negative, so this has a positive charge, and is supposed that to have a electron which is a negative electron. We discuss more on this soon. So decay process zirconium 95 undergoing beta positive decay. So we have a zirconium which is Z, we're going to put the Z, and we have a 95. Atomic number is 40. When you do this, you get this is 95. Then 40 minus 1 with 39, and we have something called whitenonium, I think, Y. Yeah, don't know the name. So it's Y. And plus, you have 0, 1. And now this one is the neutrino, not anti-neutrino, so we made it like this, not the dash on the out of them. So that's how you can make the beta positive and the beta negative decays. Next, we have a gamma decay, which is very easy. So usually after an alpha decay or a beta decay, an atom is in very excited state and has quite bit of energy that it wants to release. So after both decays, that atom has very excited state and they quite a bit of energy that they want to release. The easier ways for it to do this, that is to emit the electromagnetic radiation in the form of the photon and the gamma ray. So the easiest path is that to release electromagnetic radiations. So that electromagnetic radiation is done by the interference of photon and the gamma ray. So that's how the gamma ray is there. So as we only release energy in gamma decay, the number of particles do not change. So A and Z remain constant along with the element. So there is only energy transfer, only energy releasing. So there is no any change from this A to Z. They remains the same, but we have to do some gamma thing that we have to put that this is the equation for this. We use that star small on the X, denoting element is an excited state, that denote that every time if you made any gamma decay equation, gamma decay process, you have to put a small star on that. And this sign represents the gamma ray. Unlike alpha and beta decay, gamma ray releases electromagnetic radiation, not the particles. They only release the electromagnetic radiations, not the particles. Gamma ray is very high frequency. We all know that, we discussed that in the theory in the previous lesson, and has the ability to penetrate the most dense of the matter. That's the whole thing they repeatedly say. We have example for the gamma ray. Do you get that type of examples? Not do you have some equation, because these are the simple equations that you have to just copy the same thing, not anything else. So we have a different type of experiment in that. An acyclic diisophrenium 152 atom undergoes gamma decay by releasing a photon of energy 2.928 MeV to undergo lower energy state. Write the decay equation for this and calculate the wavelength of the emitted photon. So this is a gamma decay undergoes. So dy, this is noted by dy. So we write dy 152. This has atomic number of 66. We have to put the star on this. Is the gamma decay undergoes, and we get the same thing. And we have this thing. This is something like that. So that's all you can make. And now we have to find the wavelength. For wavelength, E is equal to hc upon wavelength. So hc upon energy. This is the energy of the photon, and I think energy of photon is given to us light over there 2.928 MeV. You have to convert this to EV. To convert this, so 2.928 MeV into 10 raised to power 6 EV upon 1 MeV. MeV cancel. You get the energy of about 2.98 into 10 raised to power 6 EV. So you have to put this over there. So this should be in EV, your Planck's constant, because EV dot second, because your energy is in EV. EV dot second, 3.0 10 raised to power 8 meter per second. Divide this by 2.928 into 10 raised to power 6 EV. When you calculate this, you get about 4.242 into 10 raised to power minus 13 meters. So this is your wavelength you have to find. So that's the thing you also have to make, because they mentioned you have to write the decay equation for this. So this has 4 marks. You have to do that equation and then solving. So that's the whole thing. Types of data decayed, and we enter copy data decayed with the theory part, with the types, and all the thing. So that's all for this lesson. In the next lesson, we'll do some graphs thing. Not very difficult graphs. We have just the graph overview of the alpha decay, gamma decay, and the beta decay. So this is all for this lesson. Like me, so we EduVibe, learn smart, not harder. Please like and subscribe to my channel. If you have any questions, let me in the comment section. See you in the next lesson. Till let's get it with EduVibe.